This episode is sponsored by NordPass.
The tradition of great national laboratories in the United States and their equivalents worldwide tells a story of scientific discovery and thinking that have led to major advancements in science and technology and our understanding of particle physics and the universe at large. These places are also sources of new ways to think about other areas of science, including SETI. My guest today is an astrophysicist long involved with SETI based at one of the great national labs, Fermilab, and today he tells us what it's like working at such an institution.
Welcome to Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. James Annis. Dr. Annis is a senior scientist at the Center for Particle Astrophysics at the Fermi National Accelerator Laboratory. His current research is measuring the parameters of the cosmology model using clusters of galaxies, the weak lensing they cause, and their effect on the cosmic microwave background. His research also includes measuring the local expansion rate of the universe using optical observations of gravitational wave sources. He joined the Sloan Digital Sky Survey in 1993 as a postdoc. He helped found the Dark Energy Survey in 2003.
James Annis, welcome to the program.
Well, thank you. Thanks for inviting me. I was here when we discovered particles, top quark. It's exotic. I don't know about you to have that experience in your history. We discovered the top quark here in 93, 94. This is essentially a reservoir of scientific and engineering talent that, since its foundation in 1967, has been aimed at making particle accelerators. We've mostly been aimed at the highest possible energies, because in high energy collisions you get new particles. In the last 5 to 7 years, we've transitioned into following the signal. The signal in high energy physics seems to be neutrinos. Neutrinos are exotic in many ways and seem to be beyond the standard model in some ways. And we've now transformed our high energy particle accelerator into a high luminosity proton beam. We take this very intense proton beam and slam it into a steel barrier, making it very radioactive. And out the back comes the Neutrino Beam. And we use that to study neutrinos both locally and in mines in South Dakota for a big project called DUNE, which will be the world's best Neutrino Detector. It'll be online in about 8 years. That's not actually my job. I'm just a spectator for this. My job is cosmology. It is surprising but true that there's this deep connection between astronomy in the form of cosmology and high energy physics. It's surprising because there's no such deep connection between particle physics and chemistry, for example, even though they're adjacent fields. They don't talk to each other particularly. But in cosmology, if there's a new particle that's massive and common, it affects the cosmology that we measure, and vice versa. If we measure something in the distribution of galaxies that suggests a new particle, a new lightweight, massive particle, that high energy physicists can tell us, no, we've never seen that, it can't be true. Or, oh yes, we know about that now that we looked where you told us to look. It's very exotic.
Now, you mentioned a neutrino detector, very sensitive one. And to tie this back to cosmology, would this thing be able to detect the type of neutrinos that would come out of a supernova when the supernova event occurs? Would it be an early warning device?
Yes, it'd be a very good one. It would detect things all the way to the Large Magellanic Cloud. Actually, that's a no-brainer. They did that in 1987. I did that project. I don't think it reaches M31, the next big galaxy over. It's one of our cubed, one of our squared, and things get messy very fast and you don't have enough. But unlike in 1987A, where we detected, I think, 7 neutrinos in the IMB detector, this thing will let you look at the energies and time distribution of neutrinos of supernovae in great detail, actually. You'll probably get to watch the formation of the neutrino sphere and its decay away. It will be really, really cool when the next galactic supernova goes off. And I got to tell this story. I talked to you about the big neutrino dump where we fire our proton beam at a steel wall.
Yes.
That glows in neutrinos just like a supernova. The same energy scale and the same, very much dimmer, but it has the same thermal distribution of neutrinos as a supernova. If you could see it, it would look like a supernova. And it's just a building out on site. Yeah, it's very intellectual, but it's true.
Now, can you, with that neutrino beam, can you detect that on the other side of the planet if you directed it towards Australia or something? Could they? They should be able to detect the neutrinos, right, through the planet.
Yep, we do. We go through the planet. So we're aiming at South Dakota. I didn't do my homework. We're aiming at a mine in South Dakota where we're building the dune detector. It is significantly underground in an old mine. So the neutrino beam is aimed not quite down, but certainly below the horizon here at Fermilab, because the curvature of the Earth is significant enough that it rises back towards the surface and hits the abandoned mine. There's also, related, the IceCube high-energy neutrino detector in the South Pole, they use the Earth as part of the detector system because neutrinos go through the Earth without a problem. The cross-section of the Earth is not high than neutrinos. So we produce huge number of neutrinos, and we have to have a very large instrumented, basically water space, so that we can see the neutrinos interact with the water. IceCube does it with Antarctic ice. We do it with liquid scintillators.
Has anybody tried to communicate using neutrinos that way?
In the sense that you can tell the beam is on at Fermilab, yes, but not in the way of actually sending a message. We can actually detect neutrinos. We know if the beam's on. That is a communication. Is the beam on? Yes, we're seeing neutrinos. It's not a very good way.
Yeah, I guess the best you could probably ever do with something like that is Morse code.
Very low baud rate Morse code. Yeah, you probably.
Very
so
low.
we do chopping. We use pulses of. So the way our particle accelerator builds up a proton bunch, it does them in bunches, and then throws the bunches at the steel wall. That essentially gives you a pulse signal. They hit the steel wall probably every 100 milliseconds. And so that pulsing itself allows you to do things like look for signals on and off, looking for what the cosmic ray rate is during the off signal, and looking for the signal itself, the neutrinos, when the pulse is hitting the steel wall. So that pulsing is a variation could be used for Morse code.
Now, what about interstellar communications using neutrinos? This is an old idea that, maybe radio isn't, which I can't by any means envision. Radio is just ridiculously useful, and I would imagine civilizations use it for their entire existence. But what's your view on neutrino communications in SETI?
It is difficult to detect neutrinos. It's a non-optimal way of communicating. The nearest analog I could think of is you can use radio to talk to submarines, but you need long wires, long of a wire behind the submarine as you are below the surface. It means the baud rate the information transfer rate is very low. And we don't, I'm sure the Navy uses it, but I don't use it very much because it's just not efficient. The analog with neutrinos is you need vast detectors in order to detect enough neutrinos to get a signal. And when we are talking about intergalactic distances, it seems you need supernova scale neutrinos to do it. Very energetic events in neutrinos. Energetic means high luminosity. Huge numbers of neutrinos come out. In the galaxy, usually beams work better than 4 pi, just scattering neutrinos everywhere. You can put more neutrinos in the beam. But if you're going to use a beam, you got to know which direction you're pointing in. I bet they could do the navigation. They do ahead of time to aim at a star, right? So when it gets dark, rotates, moves into the beam when the beam gets to it. That doesn't seem to be a problem. But choosing which star you want to target seems to be a problem to me. if I was going to do that, I'd probably aim at a globular cluster where the star density is super high. It's a very inefficient technology. I mean, so is gravitational waves. They're both very inefficient technologies for data transfer because the signals are either hard to detect, and these gravitational waves, they're hard to produce. Neutrinos are pretty easy to produce, actually, but they're just super hard to detect.
So it becomes the proverbial situation of fire. Even though humanity has had fire since the very beginning, and in fact, other proto-humans, human relatives had it, we still use it. And fires are still everywhere. And very likely we will still be using fire 10,000 years in the future, just because it's useful for what it is. And radio seems to be in the same boat. You know, sure, you have other ways you can hypothetically communicate, but why bother with gravitational waves? You'd have to be moving around huge masses.
Neutron stars, basically. It's tough.
Yeah, so it's much better to just send a radio signal.
I mean, it's plausible you could build a beacon of a supernova in some way, neutrinos.
Actually, there was an interesting paper about that one way that might make sense in SETI is if you really want to announce your existence, wait until there is a supernova and then transmit your signal when everybody's looking at that supernova. And that they anticipate it's coming, so everybody starts observing that supernova, and then all of a sudden an alien signal comes through that says you are not alone.
Yep. You have like at least a month. I mean, supernova have this feature that's long-lived. So you have this light beacon that lasts for 30, 40, 50 days. On the other hand, you have to wait. I mean, try imagine engineering that. You're another civilization. So you like Betelgeuse. We know Betelgeuse is going to go any day now, but it could easily be 50,000 years before it does. And so you design a system where you're ready to send your signals, waiting for that supernova to go off, unless you can cause it to fire off yourself. And 50,000 years is a very long time scale for civilization activities. But yeah, exactly.
Still might make more sense, though, than building a gigantic, energy-hungry, omnidirectional beacon that you have to keep running for centuries. It still seems to make a little bit more sense than that.
I mean, so type 2 supernovae, type 1 supernovae, where you're doing the mass transfer, I bet you could help that along. That'd probably be my choice for that. The type 1s, you can see when the white dwarf's about to explode and help along the mass transfer. Civilizations like doing things. So if you're helping the star to explode, you can actually time everything.
Now, on your homepage, you mentioned the 7th floor of Fermilab's Wilson Hall, home of the experimental astrophysicists. Give us an overview of what you guys are doing and what's the future for Fermilab.
So first of all, what's the past of us here? So like the first project we did as a group was a Sloan Digital Sky Survey, which in its day was absolutely revolutionary. I mean, we took a map of quarter of the sky in images and got a three-dimensional map of 1 million galaxies, put it all in the database, and let people anywhere in the world use it for any science they wanted to. With high accuracy, calibrated images, fantastic spectroscopy of all the galaxies, a lot of stars, a lot of quasars. A fabulous, fabulous experiment. It's still going on, but mostly it's a stellar spectroscopy experiment. We moved out of it after about 5 or 10 years of data taking. We moved out of it. We moved over to a project called the Dark Energy Survey, which is sort of like Sloan was a 2.5 meter specially built wide field telescope with brand new spectrographs and brand new world's biggest camera on it that surveyed the northern sky. We decided we wanted to go much deeper over a smaller area. So we went to a 4-meter telescope in the southern hemisphere called the Blanco telescope, an Apollo-era telescope. And we put on a giant camera on it, like 1 meter across, of exquisite silicon that was very red sensitive, and did a deep imaging survey over a quarter of the sky. The Sloan was basically the world's best control sample. You want to do a census of the local universe. And we also discovered baryon acoustic oscillations in that experiment. In the DES, we were more aimed at measuring dark energy, trying to measure the equation of state of dark energy, what its redshift evolution was. And we, in the end, are using a combination of weak lensing and galaxy distribution function. So we look at the galaxies, the way it's distributed in the sky. We look at the way the galaxies distort the matter behind them. That's the gravitational distortion of light passing through the potential well. So we're looking at light, and we're looking at mass, and we're looking at the relationship of the two, and that gives us this cosmological measurement. The project I'm literally leaving town tomorrow morning at 9 o'clock to go to Tucson, Arizona for the new project. It's called the Dark Energy Spectroscopic Instrument, DESI. No one ever calls it the first. They always call it DESI. It's another Apollo-era telescope, a twin of the Blanco in the southern hemisphere, but it's called the Mayall. It's a glorious telescope with a long history of great work. And it now has a giant brand new instrument, which is a 5,000 fiber spectrograph. The Sloan was 600 fibers, and the DESI is 5,000. It's fabulous. It's trying to measure the baryon acoustic oscillation for all redshifts between 0.1 and 3 using a wide variety of galaxy samples and some quasars. It's going to make this fabulous measurement of the distance scale at all those redshifts. It can make this huge improvement on cosmology. But my real day job, and what we're aiming at for the bulk of this floor over the next couple of years, is the Vera Rubin Observatory. So this is back in the southern hemisphere, not so far away from the Blanco. It's a brand new telescope, 6.5 meters. The world's biggest camera will be on it. It's going to image basically the entire night sky every 3 nights for 5 to 10 years.
I have to note here, this was up until recently the Large Synoptic Survey Telescope, now renamed the Vera Rubin Observatory.
And I very much approve of the name. It has names.
Oh yes.
The telescope is named, the survey is named, and the observatory is named. And in the old days, the prehistory, back in the late 90s, it was called the Dark Matter Telescope. And so it's very appropriate that these days it's the Vera Rubin Observatory, because she should have gotten the Nobel Prize for dark matter.
I agree. Absolutely. And I cannot understate my excitement and anticipation for that telescope, because taking images, basically an all-sky survey, as it's going to do at intervals, that is going to just reveal so much about things like interstellar objects passing through the solar system, comets, Planet 9 if it's out there. Just all kinds of things will suddenly be available to us that was never available before. You mentioned the great Sloan Sky Survey. Well, but this is doing it much, much faster and essentially as close to real time as we can really get as far as sky surveys. And I find it just amazing. So if I had to pick an instrument on Earth that's about to get first light over the next 20 or 30 years, I think that telescope is the most interesting one.
It's a challenge to pick it. It's a glorious observatory. The camera's going to be fantastic. The data set is a gold mine for sciences from cosmology through the solar system and everything in between, looking for dwarf galaxies in the local neighborhood, looking for micro-lensing of stars by dark matter candidates in the galactic halo. It's going to do so much. And after a period of time, entirely open to anyone on the planet who wants to come in and play with the data. That's underappreciated. You would think that scientific data is made available to everyone. In practice, it usually isn't for a variety of reasons, or is not terribly relevant. These big surveys, like the LSST survey, are so homogeneous and easy to use that you can do so many projects with them that there's not enough people to do the projects. And that sucks in people from all over the world to do science projects. We saw that in the Sloan. We'll see that with LSST.
Well, and citizen, the sort of initiatives for citizen science where people can look through images or anything like that. And, I know that was done with Kepler, with people looking through light curves because there was just so much. And then, of course, obviously you have computer programs and things like that that can look through data like that. But it's just mind-boggling to think about what this is going to reveal, especially when we have things like Oumuamua and Borisov, which are essentially samples from across the galaxy from somewhere else that we can look at, see, what's the geology of this like, things like that will probably be really interesting in coming decades, especially if we start finding things like amino acids, within these objects. Again, you get another clue that maybe that life is not rare, or at least the building blocks of life are not rare.
We definitely should be exploring the Kuiper Belt. And one of the underappreciated things of LSST's survey is that it will do a fine census of the Kuiper Belt, the trans-Newtonian objects, the big ice balls that are out past Pluto.
Yeah, pristine representatives of the early solar system, essentially.
And things that may be captured from outside the solar system. They're all there. They don't get boiled off by the sun. You just have to, and they're eminently visible. They're just technically difficult with our current instrumentation, but won't be with LSST survey. Those questions can be asked. The question whether there are lights on them, for example, could just be asked of a data set.
Right, yeah. It just simply look. Well, like people look at they reference the Sloan survey right now, there are lots of people still studying it, looking for things that have changed, for example, a star gets occluded or disappears or something like that, you go back to these past sky surveys to see what it looked like before. And even the photographic plates, I think some of those go back to the 1890s and were used with like Tabby Star to try and figure out what was going on there as far as dimming.
Exactly. Long time. Yeah. So we don't have a long duration plate history of the sky. We have to basically have a long duration human visual magnitude representation of the sky. It gets messy, but it's visible. It's not going away soon. We just keep on staring at the same stars over and over again for 1,000 years. We'll learn stuff. That's long duration astronomy. We're not there yet.
So what's it like at Fermilab? In the past segment, we were talking about how, cross-disciplinary communication. So do you guys just sit down with the particle physicists and chit-chat and speculate? How's it work?
Yeah, sort of. So the people who do the most cross-fertilization are the theorists, as you might imagine. They have very broad scientific interests. So right at the moment, it's the dark matter theorists. There's at least two branches here. There's the dark matter who came from what I think of traditional astronomy side, but really it's the direct dark matter search side. And they're just theorists who work on the interpretation of what possible dark matter particles could be. And there's the other side, the accelerator side, the traditional high-energy physicist theorists, who now have a very strong interest in dark matter class theories as a way of getting past the standard model. And right at the moment, it's cheap and easy to build dark matter particle accelerator experiments. Like just cheap compared to most IG physics, and cheap compared to my cosmology experiments. So right at the moment, those two branches of theory are talking to each other every day. They have these lunches. We have ours on Mondays. The theorists, I think, meet on Thursdays. They have these seminars they both go to. The closer you get to the experimentalists, the more parochial we'll be. We'll stick around the people who work on our experiments. But there are mechanisms, basically coffee machines. Where the coffee machines are, the scientists show up. And there's always chalkboards or whiteboards next to the coffee machines. And so you go get coffee, you end up talking to people and start writing on the, actually works extremely, like the watering hole. It's not water though, it's espresso. The espresso holes work great here.
Interesting. So you can attract the scientists with a coffee machine and a chalkboard.
Yeah, we might need a hot spare espresso machine in case one breaks.
Yeah, and an extra chalk as well.
Yeah, the chalk's a thing. So some of the people write on their windows. So I don't know if you've ever, the physical architecture of Fermilab is really interesting. The main building is a 15-story skyscraper that basically is two sides separated by glass. They're sort of leaning on each other at the top. This big atrium with glass walls on either side. And so each of the sides of the skyscraper have offices, one side of which looks out at the prairie, and the other side looks across to the other offices. So we get to see each other, but there's glass when we're looking at the people across the atrium. And some theorists will work on their windows with whiteboard pens because it works. It's very Hollywood, in fact, that people are doing it.
Do people write messages to each other on the glass?
Aware of. Although I have to tell you the story. It's sort of a message. This was 20 years ago. I was in my office late at night working, doing something on the Sloan Digital Skies, and I was on the 6th floor. We moved to the 7th about a decade ago. And I looked across the window, and I saw one of my coworkers walking along the ledge on the other side. And it occurred to me that was a ledge on the other side. We're on the 6th floor. He has a 6th floor drop-off. Turned out that it wasn't quite 6 floors, there's 3 floors. But he had crawled out the window, was walking on a ledge to go do something. That's a message. That was a message to me is, what are you doing, Ron? Get off the ledge.
So, hopefully he safely got back in the building.
It was only inside the building. He just had to get back in his office. Back in the 60s, the late 60s, there was enough money that you could have an aesthetics budget, small amount, a few percent. And they spent it well on the architecture here. They did a wise thing and made it architecturally appealing instead of just cubes of cement and brick someplace. And it's a really interesting place to be in, just physically being here. There's trees and plants in the bottom of the atrium where the cafeteria is, and looking up 15 floors to the top in the middle of the atrium is sort of awe-inspiring as is walking down the exterior staircase from the 15th floor down to the 1st floor.
Now, I've seen pictures, and let me ask you this. I've seen pictures of the building, and speaking of that aesthetic budget, does that inspire you in your work? I mean, when going into such a building, does that sort of get you pumped to work within astronomy and astrophysics? Is it conducive? It's sort of like an old university, like Harvard, with really nice buildings and things like that. Does that actually help to inspire you in your work?
So the old buildings have their own. It gives you a sense of tradition and long time scales. This feels very modern in a good way and not a brutalistic way. So the Fermilab site is open prairie. They're trying to recreate the prairie. And you're driving across it for 10 minutes to get from the boundary to the high rise. The high rise is a single thing reaching up into the sky that's all cement and glass. And driving to it is always an inspiring moment because you work in this thing that's reaching up into the sky and yet is built on top of Particle Accelerator in the Earth that does high energy physics of the highest caliber. So you get this moment of a rush when you're coming into the building. And then when you're in the building, physically it's a great place to be. And you feel like you're a valued scientist and not just pushed into a concrete brick building somewhere. I don't know if you've ever been to Goddard. A lot of their buildings are concrete block buildings. They're great. They do wonderful stuff, and they have marvelous spacecraft. But the architecture of this place makes you feel like, yeah, we're doing great stuff, and you should come here to do great stuff with us. It's wonderful.
I kind of wish that 1960s futuristic architecture would get revived because, you look at examples like, one really good example would be Charles de Gaulle Airport in Paris, where it was built, out of concrete, but done in such a way as to evoke the future. And Fermilab seems to do that as well, where they intended to make this not just a building, but an edifice to, in that case, science, but also the bold march into the future. And I kind of wish they would revive that architecture, actually, especially in days like where we have SpaceX and things like that.
You can see it in telescope architecture too, in the domes. The two I was talking about, the Blanco and the Mayall, they're glorious. It's hard to describe. They're 30 meters tall before they get to the platform that the telescope is on, and they have interesting angles in the panel work which makes up the exterior. So when you look at them from the outside, it feels 60s, but it feels like this is high tech, the future. This is a fabulous telescope. And then you go to a superior telescope on the same site, and it's just a box, cheap as possible, and very highly engineered to have a low thermal footprint so that doesn't affect the seeing, which makes it a superior telescope, but it doesn't look very interesting. There's something to be said for an aesthetics budget, which inspires the scientists to use the machines and inspires them in their places of work to do things that make the future. I wish we would back to that.
I wish we would too. Architecture just got boring for the longest period of time there. I wish we would sort of get back to that, especially if we ever have contact with an alien civilization, because they're going to say, what happened to your architecture?
What did you do?
Yeah, what have you done? It was so nice, and now... All right, Jim, it was a pleasure talking to you again, and best of luck in your work.
Sure, thank you very much. It was a lot of fun.
John, have you checked your emails lately?
No!
Why not? Your inbox is currently at 12,422 unread emails.
For corn's sake, I can't figure out how to get into my email.
And why is that, John?
I forgot my password.
Well, it's a good thing NordPass is our sponsor this week. NordPass is powered by NordVPN, the cybersecurity professionals. With NordPass's autosave and autofill, you'll be able to log in to all of your accounts with just a few clicks. And with a password generator, NordPass generates secure and complex character combinations instantly and provides optional two-factor authentication. With NordPass, you'll get 24/7 customer support and a risk-free 30-day money-back guarantee. All of our subscribers can try it today. Go to nordpass.com/Event Horizon and use coupon code Event Horizon for 50% off NordPass at only $2.49 a month.
That sounds perfect.